We are recording again. All right, so we got our weird readings when this thing's running. How often are you going to test this thing while it's running?
Zero.
No, that's not true. Not zero, just not very often, okay? Sometimes there may be a fault in it where you want to see, hey, maybe it's an open circuit, maybe something might get a power, whatever it might be. But there's going to be test locations and the manual is going to tell you when to do it. If we get bored downstairs, fat chance, I'll set up the Prius and I'll actually show you these measurements, okay? So, let's shut the system down, right? All of our measurements should be zero, right? That's what we are looking for. 10 volts or more is unsafe. So if we do a test at this location, after waiting our appropriate time, the MSD is released, the car is commanded off, all that kind of stuff, and we test there and it's 5 volts, it's still considered safe. At that point, you could take off your gloves once it's shut down and work on anything outside of here trouble-free. So far, so good, right? So, we shut it down, we're hoping for zero, and we see this. Except the battery is open. Is the battery the source of this in this scenario? We see 400 volts, but the battery is actually disconnected. The battery worked properly, bang. Everything shut down, you remove the MSD, so there's an open circuit there. Is the battery responsible for that measurement? 400 volts and the battery is turned off. Open circuits everywhere through the battery.
I would guess it was the DC to DC converter.
It's not. There's nothing in the DC to DC converter that can hold that type of energy.
So would it be in the logic?
Not in the logic, in the thing the logic's attached to. The inverter. The inverter, whenever we drive one of those coils in the motor, remember how I said it's really, really low resistance? Almost a short circuit. And if we just had it configured like this, and we started driving those coils, we would get massive dips in the pressure in the system. We get these massive drops in voltage. We can't have that signal going up and down and up and down. We want a real consistent voltage. Come on a trip with me all the way back to the 90s, maybe even the early 2000s. Spec car culture was at its peak. We had huge wings and underglow and wild paint jobs, like just insane stuff. Mini trucks, everywhere. I love mini trucks. They were great. Astrovans, and what would we put in the back of Astrovans? Massive stereos, huge. So we've got our little trucks, we've got our little cars, we've got our little vans, we've got these giant stereos in them. And if you were there, man, we wanted everything to just, when the bass dropped, we wanted the license plates to fall off, the windows to blow out of this thing. Boom. However, if we hooked that directly up to the 12-volt battery, every time Dre dropped a beat, oh man, the lights would fade out, the stereo would cut out because the voltage would drop too low, because the resistance inside that driver was like 2 ohms. There's nothing, right? So we were shorting out the battery. Can you imagine if we did that on a big system like that? Oh. So what was our answer to these sick beats coming through a giant subwoofer with an amplifier? How did we protect the 12-volt electrical system? How do we reserve enough pressure to hit that low note? To really pound. Any ideas? How do we hit that hard? Just a boom, and just let the windows rattle. We used to use what they called a cap. It's a big cylinder, and it would show your voltage level right on top of it. Well, it wasn't Cap America, so that's the wrong cap. It was a giant capacitor. Capacitors store voltage, but they do it temporarily, right? They're not a long-term storage solution. In order to compensate for the short circuits that I create when I power up the magnets inside of the motor, inside of here, I have a whole bunch, I'm just going to draw one, of giant capacitors. The capacitor acts like a battery, and I measure it back here. I'm measuring to see if the capacitor is charged. Not if the battery is open. The battery circuits probably are open, unless I throw a contactor code. If I measure here and there's still power, it's probably this guy here. There's a whole bunch of them in there. And if this system is 400 volts, those capacitors may actually be higher, much higher. There is a boost circuit inside of the inverter to increase the voltage on the AC side of the system. More pressure to drive the motor. It overcomes counter electromotive force. We'll get into that later. All right? So when we shut the thing off, what are we really looking for when we test the high voltage system? We're looking for residual energy in the capacitor. Leftovers. There should be in this system a shorting circuit. So when I turn off the key, active shorting should close a switch, which bridges my positive and negative together, goes through a resistor, so it looks kind of like this. I'm going to add another circuit here. Move over, logic, we know you're attached. So, that switch closes, we're disconnected back there. These resistors will dissipate the energy that's in there. Should take milliseconds. Shut off the key, battery opens. Is a battery source of power once it's open to the high voltage system? Nope. So if the battery's open and we close this switch, shorts positive to negative, makes these nice and hot for a split second, we get rid of that little bit of voltage, then my system should be zero. If this switch is broken, could this hold power? Yeah.
Is that why the electric excavator down there shuts, the power dissipates faster? Because of all the
This is what
implements?
makes it, yeah, this little shorting bar. As soon as you shut it off, it closes and dissipates all your capacitors.
And because of all the implements on it?
No, it's all right here. Really, realistically, in a vehicle, the minute you shut off the key, that thing shorts out the system. Those capacitors should be shut down, like there should be no power in the system within a few milliseconds after a key off.
Well, we noticed the difference between the car, it takes like 2-3 minutes for the power to drain out, but on the excavator it takes seconds.
Did somebody put a meter across so you could see it?
That was what it said in the service manual.
Oh, did it? Wait 5 minutes, right?
No, it said seconds.
No, on the cars, wait 5 minutes?
Yeah.
It's a redundancy. It's in case that doesn't work.
Well, why
If you
did-
shut off the car, I'll put the multimeter on the Prius for tomorrow, right? And we'll watch it. It'll go from 400 volts to zero. Basically, as soon as you can think about it, boom, zero.
So why would you have, why would the service manual on the car say you have to wait 5 minutes and the service?
One of the switches broken.
But the service manual on the excavator that.
Because you're dealing with 48 volts.
Okay.
Yeah, you're dealing with 48 volts, I'm dealing with 400.
You think that would need more volts because it's so much bigger and more implements?
Why they did 48 volts, I have no idea. You would think, but that thing is lower voltage than a car. Way lower.
But it has more power than torque.
Has more torque. Doesn't mean it's got more power. Right? Why they did it, I have no idea. It's probably for simplicity as well as serviceability when you don't have tools or safety plugs or whatever it is. Or it could just be that, hey, they wanted to market a 48 volt system to make everyone feel warm and fuzzy. But if you get into mining equipment, you're 7,000, 8,000 volts, whatever it might be. So voltages are gonna be all over the place, just depending on the design of the vehicle and how they implemented it.
So now we added the, hydrogen electrics.
Oh, we're not even on hydrogen electric. All the hydrogen is used for is to run a fuel cell and we're to charge a, energy storage system like a battery. That's it, that's all it is. Toyota Mirai runs on hydrogen, runs a fuel cell, charges a battery, drives a car. That's it.
Which is better, the electric or the hydrogen?
They're the same.
So you-
Hydrogen has fuel cells, that's it, that's the difference. It's got an auxiliary system that charges the battery as you drive it, that's it.
So does it take away the room?
No. No, now you have massive hydrogen tanks underneath the vehicle that you have to accommodate for, and fuel cell stacks they have to worry about. So the battery weight goes down, but the accessory weight stays probably like the same. You fill it with hydrogen, maybe it gets lighter, like a Zeppelin. Right? So, this is the danger that we're looking for, is really the takeaway here. It is the capacitor in the inverter that we're testing for when we do a shutdown. Yeah, we want to make sure the battery is disconnected, but look, 1, 2, 3 disconnection points. How many disconnection points do we have to the capacitor? 0. That's a dissipation, that is not a disconnection. Make sense? Cool. Cool. So, now we know that there's a danger. That's the danger that we're testing for. Let's flame this system up again, okay? So that switch is open, the shorting bars are open. There's 2 shorting systems in there. There's the active shorting system that'll dissipate in moments. There's a passive shorting system. You want to see the passive shorting system? So if this is active, right? It's got a switch that'll actually close. If that thing fails to work, would that dissipate energy as well? Yep, there's a passive system. So the computer can discharge the capacitor, which is going to take longer because the resistances are higher. It doesn't make the current equalize as quickly, or the voltage equalize as quickly. Crazy. How's everyone's mind doing? You making bacon? Frying it? Cool, let's keep going then. We're gonna make pounds of bacon today. Thick cut, the good stuff. Okay? All right, we flamed the system up. It's running again. Except this time we've got a problem with the system. Let's insert a problem. Oh no, we've got a short circuit, a loss of isolation. Is the car going to shut down? No, why not? Might keep running. We've got a dead short to the chassis and the car's like, cool. Is it still safe to operate? Yeah, it can't make it to the negative bus. It's fine. It'll keep driving down the road. It's not going to shut off. It can see it because it's got the computer in the inverter and it's going, man, this is bad stuff. So it's going to turn on your service vehicle soon light. Is it going to turn on a check engine light? Can an electric vehicle use a check engine light? No.
No engine.
No emissions. A check engine light is for exceeding federal emission standards by 1.5 times. If I have a loss of isolation, am I hurting my emissions? No. So it has to have its own light. They're new and special. Ooh, I will add all of the first year resources in this afternoon, and if I forget, yell at me tomorrow morning, okay? So you can see all of that information too. So, can't have a check engine light, fire on the regular light, but the car might keep driving. Cool. You come to this thing and we've got our classic code. You ready for our code? What is our code? POA6, P0A6. It's all angry, right? It just set, it didn't have time to tell you where it was, so you didn't get no symptom, whatever it might be. You decide that you're going to diagnose this thing. You could get out the Megger. We'll get to the Megger. But you got the car running. You got your multimeter out anyways, we're gonna shut the thing off. You got your high voltage gloves on, you got your face shield because you're dealing with live high voltage at this point, right? All right, let's hook up the meter. Let's see what's going on here. So, your first measurement, positive to negative. Are you gonna see 400 volts? Yeah, the battery's working. The car's working. There is a difference in potential. All right? The second reading that you get though, remember the car's running, it's turned on. Zero volts. How come there's 0 volts on the positive? Oh man. Zero volts on positive. What is a volt? Pressure, right? When I measure with a voltmeter, what am I looking for? A difference in pressure. What is the difference in pressure between this cable and this chassis? Right now. What's the difference between this cable and this chassis? Difference in pressure. Remember, there was a difference in pressure before because there was a resistance, right? Did that bypass this resistance?
No, it became a resistance.
Is it a resistance? No, it's short circuit. Basically, the question becomes, what's the difference between positive and positive? Nothing, right? There is 0 pressure differential because we created a short parallel circuit. Do you see that? So instead of the meter going here and measuring the voltage drop across there, now it's going and there is no voltage drop. It's the same potential. It has made the chassis the positive instead of the middle point. So if the chassis has all the potential of the battery, what's this reading going to be? Yeah, 400 volts. Volts. Because the entire voltage drop through the logic circuit, remember it's got a short here, so it can just go. So the entire voltage drop is there. So this will show a drop of 400 volts, and this will show a drop of 0. Just like that, okay? If we were to put it into kind of layman's terms, simple context, the voltage measured ran away from the short circuit. If I have a loss of isolation on the positive side, the high voltage reading will be on the negative side.
And vice versa?
And vice versa. So let's remove the reading from here. See my hand come up? I'm like, oh, we're going to make a mess here. Don't make a mess here. We're going to remove this short circuit. Look at that. It's so easy. And on the negative side, we're going to create a short circuit. Yeah, it's upside down. Get over it. Still a straight point, right? My readings would now be reversed. There you go. Because it basically went here, through this resistor, through this ground, and over here. See how we bypassed that resistor entirely? Right? So I've got all my potential drop here, none of the potential drop there. If I touch the chassis now, and this cable, am I at risk? Yeah, because this got long arms, it's really good. Right? Touch the chassis, now he's got a risk. Now there's potential for injury. How often are you going to touch the inside of that cable? Just driving the car along? Never, right? Never. But we know what measurements to expect if we start to lose. If there's a resistance in the line, let's say it's, I don't know, oh God, 5 mega ohms. Is that going to be 0 here? No, because now it's dropping something, right? You'd have to do parallel circuit math. Who wants to do EIR math? Me neither. So we're going to say this might be 100 volts and this might be 300 volts. Still higher voltage, right? Which means the problem is on the low side, the negative. The voltage runs away from the problem. Were you ever young once? Do something terrible? Throw a rock through a window? Scratch your parents' car with the handle of your bicycle after they told you not to? Right? What do you do with the problem? You run away from it. You are pressure. You are voltage. You run away from the problem. Voltage is no different. It just scratched its parents' car. It's out of here. It's going to the other side. Right? Short circuits need. Okay, so some pretty crazy concepts so far. Let's keep going with our crazy concepts. All right, let's add to this. I'm going to remove my short circuits. I'm going to fix my problems, okay? Hi, little fella. Aha. So let's add complexity to the system. So far, we got a DC to DC converter, we got a battery, we got an inverter. How are they wired? Series or parallel? The DC to DC converter and the inverter. Are they in series or are they in parallel? What's that? Parallel. Yeah, right? They both have the same positive feed. They're side by side on that branch, and they both have the same negative feed. They're side by side. Right? All right. So, who cruised in today? I sure did. I had the AC on. It was marvelous. The AC on my car that I cruised in today is 400 volts. Oh. So I must use the high voltage battery if I'm using 400 volts for my AC compressor. We're okay with that? Here we go. So, AC, all right. Little compressor there. How did I wire it in? Is that in series or in parallel? It's parallel, right? All right, in the wintertime, I don't want AC. You know what I want in wintertime? Heat. In my Versa, you know how I make heat? The engine. In my Bolt, you know what it doesn't have? An engine. Oh my God. So I just freeze in the wintertime. I don't think so. So, in that car, I'm going to make heat with a heater. There we go, put the little box in there. And I'm going to add that in series or parallel. It's parallel again, right? We got another system, we just wire it in parallel. What else do I want? What other fancy things? Battery heaters, right? We don't want the battery getting cold. So we add back heat. that's old Batman stuff. If you're not of an age, you probably have no idea. You're like, he's going crazy. No, not going, been there for a while. So you got a battery heater. And we can keep adding stuff on. Who's feeling rich today? You know what we should get? We should get another motor. If I need another motor, what do I have to add? If I want motor number 2, I have to add, what drives a motor? What do you say? Inverter. Yeah, I gotta add the second inverter, right? Oh man, how am I gonna wire that in? Inverter 2. And it's gonna have all the same junk in it. This is for illustration purposes. How's it wired in? Series or parallel? It's in parallel. Look at all the stuff we can just start adding. Keep throwing it out. You get a module, and you get a module, and you get a module. Everybody gets a module. They're all in parallel. Oh man, that's easy, right? Let's simplify this high voltage diagram into something that's a little bit more digestible for a moment, shall we? All right. Get rid of this, and we're going hardcore now, so this is going to be high voltage, okay? Battery. Down at the bottom, inverter. Between them, we got a positive and a negative. We need a DC-DC. We need AC. We need heat. We also add battery heat. That heat, that heat. What do they look like? Looks kind of like a step ladder, doesn't it? It's a ladder diagram. That's your entire high voltage system there. It's just a whole bunch of modules in parallel. How are the high voltage modules wired? In parallel. Why does it matter? Do you work on cars that work properly? Yeah, you do? What are you, like an accessory guy? Trailer hitches? Bug deflectors? I did that too, it's terrible. But then you move into trim, it's like squeaks and rattles, and you just take dashboards out. They're sharper than they look, be careful, okay? We don't work on cars that work properly, we work on cars that are broken. That's kind of the whole point of what we do. So what we have to do is we have to diagnose this broken car. And we can see, oh man, from what we just experienced, the problem's over here somewhere. Where's the problem? What module is causing my loss of isolation? Can I just start disconnecting things and hope my voltage comes back up? No, because as soon as you pull the plug, it's got what they call an interlock loop. So there's a circuit in there making sure that plug is plugged in. And if it's not plugged in, oh boy, this stopped working. Oopsie doodles, right? We can't have it stop working. So we can't just start unplugging things. Instead, we have to see where this loss of isolation is without pressurizing the system. Not from the big battery anyways. Can I use a multimeter to find a short circuit in a high voltage system? No. I need a magnet, right? that little box that makes 500 volts and jams it in? Cool. So we shut down the car, we get it ready to service. I'm looking for my short circuit. Where do you want to put a short circuit? What module do you like? Pick one. AC, perfect. So the AC has got a loss of isolation right here. It's got a little resistance in it, but it goes to ground. Right? We don't have the code for AC. We can see in the diagram that I just drew, that's where the problem is. But when you get to the car, do they give you a diagram that points out where the problem is? No! They don't get that lucky. So, I have to figure this out. My megger becomes a battery. Not connected. Capacitor way down there. I'm going to test my megger. Can I read open? Can I read short? Now I can test the circuit. If I test, so we'll put my little megger box right there, and go from the circuit to the chassis. And it's going to read, is it going to read good or bad? Negative side right near the short circuit, it's going to read bad, right? Bad. B-A-D, bad. Okay. So I found the AC's the problem. And I just want to make sure, so I go over to inverter 2, I hook up my megger, I put it to ground. What's it say, good or bad? Bad. And then I hook up to the battery heater. What's it gonna say? Bad. Bad, 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 bad. Oh my God, I gotta order one of everything. Do you? Why do they all read bad?
The first one read bad.
The first one read bad.
Well, the power ain't getting past the first one.
Oh, hold on, no.
First.
We go to the DC to DC converter, I read here, bam, here, we'll put the box in here, tied to ground, and you guess what it says? Bad! Bad, 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 bad! Everywhere, everything's no good. Look at the diagram, is everything no good? Why is it bad everywhere? Okay, here's a question. What is megger? It's battery, right? It provides pressure. Sees how quickly that pressure comes back. It's looking for resistance. And then it calculates it, shows it to you. It applies pressure here, it goes through this wire, comes up here, goes right to ground, goes right back to base. Goes up this wire, goes to ground, comes back. Goes from here, goes back, goes from here, goes back. They're all going through the AC compressor. However, because they're in parallel, there's no resistance on the negative side between any of those components. They all share the same cable.
So it's like a set of Christmas lights.
Bingo! It's like a set of Christmas lights. Yeah. Well, they're in series, but kind of.
You take one light out.
Oh no, the other ones will keep running in this one. But there it was, I saw the light bulb. Whenever I test one of these pieces, they can't be connected together. If I'm using the megger, the component has to be electrically isolated. So you're testing one thing. If it's not electrically isolated, if it's still attached to the car, you're testing everything. anytime we use the megger, the component has to be isolated, or you'll get a false reading. So if you didn't start here, if you didn't start at the AC, we had it connected, right? You're like, oh, I think I know. The last time I saw one of these cars, it needed a battery heater. You tested the battery heater and it goes bad. You fire a battery heater in it. When you fire the car up, is it good? No. Because when you tested the battery heater, you were testing the inverter and the heater and the DC to DC converter and the battery and you tested everything all at once. So it says bad here, you fire one of those in it, you spend $1,000 in dealer's money, put it back together, is the car fixed? No. How much time did it take you to get to the battery heater? Oh man, you had to take the floor pan out of it, get underneath there, disconnect the what? Oh man. Think with the time, and then you bleed the coolant, you got to jug the coolant into this now, you snapped a fastener. Like it was a bad day at work. You put it back together and you didn't fix it because you didn't test it properly. Anytime you test a high voltage component, it must be electrically disconnected or isolated from the rest of the system in order to get a valid result. Neat. The other thing, so you took your megger, you got all excited. You know what? I think there might be a problem with the inverter. I'm going to test the inverter. So you did it right. You came along, you disconnected the inverter from the system. No problem, right? Boom, it's disconnected. You grab your megger, you hook it up. You're like, you know what? We're going to go from this test point. There we go. We got our megger box. Attach it to the case. There we go. You hit it. Doesn't matter the test result. You just hit it with 500 volts. What did you do?
Charged.
You charged it. When you are using a megger, your gloves have to be on. It's not because the megger makes 500 volts. It's because the megger can charge the capacitor, and the capacitor can hold enough current to kill you. The megger just makes you feel funny. Unless you got a heart condition, then it makes you dead. The capacitor inside that drives a car that's, oh, let's go EV Hummer, 9,000 pounds, but it drives it as fast as an old 911. That's got some serious kick to it, yeah? You don't want to bare hand that. That'd be a bad day at school. Right, you'd learn the lesson then you'd forget everything. So, gloves on. When you're done testing a component, you have to test it out. Same as when you shut down a car, except it's on the little box on your bench. Live, dead, live, dead. Next test question that we have here, not that it's a test question, but it's a question about testing. Do I need to, when I'm testing a component with the megger, go negative to positive? So if I have the megger, I got it set to 500 volts, and I go positive to the case, right? Because I'm looking for a ground, a loss of isolation, short circuit. And then I go negative to the case. Do I have to go negative to positive on that item? For the test, do it? And here's why. I'm using the megger to look for a short circuit. If I go through a motor or a heater, is that a heater specifically, is that circuit complete? Yeah, the heater is just this. Watch. Ready for the heater? The heater there's nothing fancy inside a heater. PTC heater is just a big resistor. Should that circuit be complete all the time? Yeah. If that circuit opens up, is that a loss of isolation? An open circuit is not a short circuit. I'm looking for that high voltage system to be shorted to the ground, to chassis. I don't need to test from positive to negative in a component. That's only when I'm testing it to see if it's got voltage. If I'm introducing voltage, I only want to see if it makes it between the cable and the case. That's it. So I don't need to go negative to positive. Not going negative to positive also reduces the risk that I charge a capacitor. Alright? So I should not be going positive to negative with Megger unless the service manual tells me to. Otherwise, oh my God, it's got low resistance because it's going through it here. And it should have low resistance. It shouldn't be infinite, right? It should actually operate a heater. Is that a lot to learn today or what? I mean, we didn't even touch the book yet, eh? Look at this, like, oh. You know where that came from? Oh, you don't even want to know. Oh. So, what is a high voltage system? Our primary function is to drive the electric machine, right? But we can run all this other stuff. Why run the heater off the high voltage? Efficiency. It's better to run it on high voltage, low current, right? It's more energy efficient. If we run it, can we run a heater on low voltage? Yeah, actually we can. Did you know that old Mercedes and some Fords and BMWs have auxiliary electric heaters in the dashboard? And they run on 12 volts. But it doesn't matter because that car's always got an alternator going, right? It can do high current. Voltage goes up, current goes down. So we actually consume less current by running it on high voltage. Same thing as the AC compressor. We consume, it's more efficient to run it on higher voltage. That's why cars went from 6 volts to 12 volts. The wires got smaller, less current, more pressure. Make sense? Okay, cool. So, we run these efficiently at high voltage. What does a floating electrical system mean? It means the high voltage should not touch the chassis, in theory. However, we discovered today that, you know what? There is logic systems in here that do make a chassis connection. However, they're incredibly high resistance. So a floating system is isolated from the chassis. Just like anything automotive, there's probably a regulation surrounding that floating system. You ready for this? It is FMVSS 305, and it says isolation must be 500 ohms per volt. Minimum. Boom. That's high resistance, right? Every volt you got in that system, you have to have minimum 500 ohms. Manufacturers do not give you the minimum. So in this particular instance, 400 volts DC, your minimum isolation would be 200,000 ohms between the high voltage side and the chassis. General Motors, when you do your diagnostic chart for 400 volt systems, starts to flag it at a loss of isolation at 10 million ohms. So this is bare minimum stuff. That's what a floating electrical system is. It doesn't use the chassis as a return path to the battery. If it leaves on a positive cable, it comes back on a negative cable. All right? Cool. The next question we wanted to answer is, how is a floating system wired? What do you call that? Parallel, right? It's just like a parallel ladder system. There's nothing too fancy about it. Easy peasy. And it's got the lemon squeezy. That's nice of it. How do we make it safe? Well, when we shut it off, we have 1, 2, 3 open circuits. Over here, we have shorting bars in order to dissipate energy in the system. That's how we make it safe. And because it's not attached to the chassis, the likelihood that you're going to touch the negative and the positive bus at the same time, down here somewhere, right? Real low. So, what is a contactor? It is a low voltage that controls a high voltage through a dual contact switch. If you want it simple, it acts like a high voltage relay with two contact points. Instead of low current controlling high current, we do low voltage controlling high voltage. Easy. What it says? What is an MSD? Yeah, it's a manual service disconnect. And what that does is it separates the battery in two. It creates an open circuit between battery modules. And remember, this is a test question I like, okay? You cannot measure at the MSD because you're going to get the wrong readings. It's going to show open circuits all over the place, whether there are or not. It's going to show you that the battery is turned off, but you can't turn off a battery. You're tickling the tips, right? Because it is connected directly to the battery cells. You should never test here. Test on the output, because we can test all this. Test back here, and these are open. You can't test the rest of it from that point, because it's open. It's no good. Some people might call that NFG. Not fine and great. So that's pretty good. What's an inverter? Well, the function of an inverter, AC to DC and DC to AC. It's used to drive the electric machine, the motor. That three-phase Y-wound, can be delta, device. How many IGBTs do we use on a three-phase motor? 1, 2, 3, 4, 5, 6, right? 6 attached positive, 6 attached negative. Okay, that's pretty good. How do we go DC to AC? Well, IGBTs. Oh, it's easy. What is an auxiliary electrical system? Became the question after that. What is an auxiliary electrical system? Not an exhilarating electrical system, that's something different. It's lower than high voltage. It's our 12 volt, it's our controlling, it's our interface, it's our computer system. Right? So we need that auxiliary system to power the computers and the touch interfaces in the vehicle, as well as we needed to activate the high voltage system. Oh yeah, without that, we're in bad shape. Bad shape. All right. How is high voltage stored? It's DC in the battery. Always DC in the battery. That's how it's stored. Why high voltage accessories? I just said it. It's efficiency, right? It's efficiency. Access to direct power. Cool. And why electrify? Just to drive a motor so we don't have to burn stuff. It's pretty good. Good efficiency. We'll get into that stuff later. I don't care too much about that. Okay. How are we doing so far? We got questions? Is our brain burned out? No? No brain burnout yet?
This will be on YouTube today.
This will be on YouTube.
Like posted today.
Yeah. Why, you want to go over the lecture? Is that exciting? There might be stuff that you missed? Maybe, eh? That's okay. That's all right, yeah. I think I'm gonna upload it in 3 parts. So I'll just upload them, send the link, upload it, send the link, upload it, send the link. So, or 4 parts, depending on, actually it's gonna be 4 parts. So I'm about to hit stop and send you all for break, just so you can kind of chill out, relax your brain. We'll look at this a little bit more, and then we'll talk about what tomorrow's plan is gonna be. I think we're gonna be in lab tomorrow, and we might kind of amalgamate 2 things. So battery theory can be super boring. You know what makes it super exciting? We're working on the battery at the same time. Open them up, have a look around, match up the picture to the piece, right? And we'll open up different batteries so we can compare them and go, hey man, this is from this and this is from that. What do you think? Does that sound better than just sitting in a battery lecture?
Yeah.
Way better, right? We'll add some concepts to it. So take your 10 minutes, we'll wander around, have your darts, whatever you need to do, and come back and we'll wind the day down, try and land this bird, okay? Go. Not today. Dude, it's 11 o'clock already. I've talked your ear off for like 2.5 hours at least.